A digital twin is a virtual representation of an object or a system. Like me, digital twins are updated with real-time data which can be used for machine learning and reasoning to make better decisions. Disturbing, but yes. And what can we do with a digital twin? Let's get into it. Well, that was odd. Digital twins are usually objects like wind turbines, and they're fitted with various sensors, and those sensors capture data and different aspects of the physical object performance, like in this case, energy output and temperature. And that live data is applied to the digital copy of the wind turbine, its digital twin. From there, we can study all sorts of potential situations, analyze performance problems, and create potential enhancements that can be used to improve the real-life physical object. Now, doesn't this all sound a little bit like a simulation? Kind of does. But digital twins are actually virtual environments that operate quite differently from simulations. Now, in a simulation, we model a system or a process to understand its behavior under specific conditions. And simulations, they are static snapshots in time. They are snapshots in time that represent predefined scenarios. But a digital twin, it goes beyond this. It's a living representation of a specific physical asset. So unlike a simulation, a digital twin is continuously updated using real-time data. That's data from sensors reflecting its unique state. So for example, a digital twin of a turbine in a wind farm can track its real-time blade vibration and temperature, predicting maintenance needs and optimizing performance. And digital twins are designed around a two-way flow of information that occurs when the object sensors provide relevant data to the digital twin, and then that happens again when the insights created by the digital twin are shared back with the original source object. While simulations tell us how things should work, digital twins show us how things are working right now. Now, there are several types of digital twin depending upon what you want to model. Let's take a look at them. And the first one is a component twin. Now, component twins are the basic unit of a digital twin. They represent individual components or parts of a system capturing their specific behavior and performance. A component twin could model the behavior of a single blade on a wind turbine, tracking its stress levels, vibration patterns, and wear over time. Next layer up is asset twins. Now, asset twins represent an entire asset made up of multiple components working together. And asset twins let you study the interaction of those components, creating a bunch of performance data that can be processed and then turned into actionable insights. An asset twin for a wind turbine would integrate data from all of its components, like the blades and the gearbox and the generator, to monitor overall performance and predict failures. Even broader, we have system twins. And system twins enable you to see how different assets come together to form an entire functioning system. A system twin could model an entire wind farm, tracking how multiple turbines interact with each other to optimize energy output. And then at the macro level, we have process twins. And process twins reveal how systems work together to create an entire production facility. Process twins can identify inefficiencies and optimize processes across multiple systems. A process twin for wind energy might model how energy is generated, stored, and distributed from a wind farm to the power grid, considering factors like energy demand and storage capacity. So we've talked a lot about wind turbines, and there's a reason for that, and that is because things like power generation equipment are fantastic use cases for digital twins. Large engines like jet engines, locomotive engines, and yes, turbines, they can benefit tremendously from the use of digital twins, especially for helping to establish time frames for regularly needed maintenance. But where else are they used? Well, another good use case is in big physical structures, like large buildings or offshore drilling platforms. Digital twins can be useful in designing the systems within those structures, so things like HVAC systems. And since digital twins are meant to mirror a product's entire life cycle, it's not surprising that digital twins have become ubiquitous in all stages of manufacturing, getting products from the design stage to the finished product and all the steps in between. And then another common use case is urban planning as well. This is where civil engineers can use digital twins to show 3D and 4D spatial data in real time, and also incorporate augmented reality systems into these built environments. Look, the term digital twin was credited to NASA's John Vickers back in 2010, but digital twins are constantly learning new skills and capabilities, meaning they can continue to generate the insights needed to make products better and processes more efficient, be that wind turbines or creepy digital versions of YouTube presenters.